So first, maybe I'd like to thank my co-authors. So Mahendra and Steve are from Deakin University as well. Steve is in the room. Mahendra couldn't make it, unfortunately. And Tim from CleanTeq, who is also my co-author. So that's the title of my paper, but making the slides, I realized it's actually maybe didn't define quite well the work that we are doing here. So really, it's the first step towards the. It's a good follow-up as well on Nick's talk. So it's looking at adding scandium into 6,000 series alloys, and really, it's the very first step of a larger research effort, which is trying to understand the effect of scandium on the ASCAS microstructure. So just a quick summary. So first, what I call state of knowledge. It's really general information on scandium in aluminum alloys, and particularly in aluminum, magnesium, silicon alloys. Bit of publicity. So this book just released in June 2018, and chapter 12, if you want a bit more, a larger review on aluminum scandium alloys, written with some colleagues at Deakin. So then after this literature, I guess, or look at the prior work, we go into the details of the results. So first, we'll look at a traditional thermomechanical schedule for wrought aluminum alloys that contain dispersoid formers. Then we'll move into trying to understand this ASCAS microstructure. So when magnesium and silicon are added to scandium zirc aluminum alloys, if we put it in that way, so it actually changes the formation kinetics of the dispersoids. So we look at this using atomotive tomography and transmission electron microscopy, and we'll also look at some solidification microsegregations. And I guess the final point of the talk is how will we homogenize these alloys, and that's why it follow-ups quite well on Nick's presentation. So first about scandium in aluminum. So scandium and aluminum, there's a eutectic reaction in the aluminum-rich corner of the phase diagram, and all the positive properties from scandium comes from the formation of this Al0.8 aluminum-3 scandium spherical dispersoids. Scandium is generally supersaturated in the ASCAS microstructure in traditional cooling rate encountered in DC casting, for example, especially if it's, of course, in the hypoeutectic composition. And then you can form the scandium dispersoids during a fairly low temperature homogenization treatment. One of the disadvantages of these dispersoids is that they have quite a high coarsening rate. So that's why zirconium is often added together with scandium to form these nice core shell dispersoids. The scandium core nucleate first, and then the zirconium then forms around. Zirconium also has a Al0.8 structure, aluminum-3 zirconium, and then these dispersoids are much more resistant to coarsening. So here it's atomotive tomography from some work done last year with our partners from UAC and CleanTeq, looking at scandium zirc dispersoids in 2000 series alloys. So here in the atomotive tomography, you can see that these dispersoids also acted as nucleation sites to form fine theta prime precipitates. Again, in these 2000 series alloys and other series, in the 5000 series, for example, scandium and zirconium are usually supersaturated in the ASCAS condition, and then initial homogenization treatment is used. So now scandium is often defined in the literature as the most potent strengthener in aluminum due to these different reasons. Here just some data collated from the literature where, so often in the literature, of course, you will have like a base alloys and you add scandium and you look at the strength increment. So if you plot the strength increment reported in some papers as a function of scandium content. You can see it's quite scattered, of course, but on average, you can get between 50 MPa to 100 MPa increase per 0.1 weight% scandium addition, so it's really significant. Now, we managed, so Steve actually in the room did this literature review, so there's not that many papers that look at scandium in 6000 series, but if we look at pretty much, I think, all the papers from what we found really in 6000 series, so with magnesium silicon, and what you see is a kind of an inverse trend. So in low scandium containing 6000 series, some strength increments were reported, but you can see actually that a lot of the work going all the way to 0.3 weight% scandium then report a drop in strength in 6000 series. So part of the reason for that, so if you look at this cross-section of the aluminum scandium silicon phase diagram, you can see that if you look at silicon first, typically in 6000 series, I mean, you will be at least 0.2 to 0.3 weight% silicon, even in the low silicon 6000 series. You can see that if you go higher in scandiums than 0.075 approximately, you will start to form this tau phase and not the aluminum Swiss scandium phase, and it's often reported to be this phase, which is an aluminum scandium silicon phase, is often reported to be detrimental to mechanical properties. So I guess just a few sentences to summarize the literature. So there's not many studies, so there's not really any systematic studies at really trying to understand scandium in 6000 series, and that's what we're trying to do in this project. Also, there's not much which has been done to try to avoid the formation of this aluminum silicon scandium phase in higher scandium containing alloys. And finally, the effect on processability and aging response, really not much has been done. So quite just a schematic of I guess, traditional thermomechanical treatment. I say traditional, so that's for extrusion here, for example. So first you will have, well, of course, your ASCAS microstructure. So this schematic initially was done for the 2000 series, where mainly scandium and zirc, were supersaturated apart from the formation of a few primary dispersoids during casting. Then you had copper segregation in the interdendritic regions. Then you could do your homogenization treatment to form your dispersoids, core shell. Then, of course, you extrude, you solutionize your copper, and finally artificially age. So, yeah, so as I said, scandium and zirconium usually supersaturate, and you form your dispersoids. So the big question is, can we do that in 6000 series with this scandium and zirconium? So now let's go to the results. So that's the compositions used in this study and in the paper. So we had a ternary aluminum scandium zirc alloy, and then the other alloy with magnesium silicon with 1% magnesium, 0.6 silicon content. So yeah, so we do our own casting at Deakin. We actually use cylindrical steel molds with a large steel base. So we do have directional solidification, and we measured the cooling rate at different, so we have cooling rate curves, and they actually compare quite well with DC casting type cooling rates. So we believe we represent quite well a DC cast microstructure. So here, so we've done some TEM to start with, and what you see in the ternary aluminum scandium zirc is that you have quite a clean microstructure. Apart from a few, you have a few primary dispersoids, also a few small coherent dispersoids, but mainly it's quite clean. And then in the magnesium silicon scandium zirc, you actually have quite a lot happening here. In the center, you can see some fine distribution. So if you look at now a bit higher magnification, fine distribution of dispersoids, this type of dispersoids. Instead, we have also arrays of magnesium silicon precipitates. And then these dispersoids, if you look at diffraction pattern here, you can index actually the subreflection to L1 to microstructure. So scandium and zirc are mainly supersaturated in the ternary, quite high number density of dispersoids in the alloy containing magnesium and silicon for same scandium and zirc content. And also arrays of magnesium silicon precipitates. So now, so in the paper, I actually had two volumes. The two volumes on the left, and then we looked at dispersoid composition, ASCAS dispersoid composition. Since then, we had another actually volume from the same alloy, which was quite different, which a higher number density of dispersoid and also some magnesium silicon phases. So we actually saw quite a lot, of course, an ASCAS microstructure, so that could be expected as well, non-uniformity in the microstructure. One of the interesting results, I guess, is that, so this scandium, these dispersoids, first we'll go into details after, the mainly aluminum, so silicon substitute to aluminum, and then scandium, so almost no zirconium in there. And then we saw in this volume on the top right that almost each dispersoid had the magnesium silicon precipitate nucleating on it and then growing away from it. So that's on the top, the magnesium scandium isosurfaces, and then you can see silicon is both in the dispersoids and precipitates. Now if we look at so just the bulk compositions of the sample, so we can see that there's some variation. So some of the bigger variation, I guess, are from magnesium and silicon. If you look at sample 1 and 2, you've got some ratios which are quite close to the bulk composition. If you look at sample 3, magnesium and silicon were actually quite closer together. And then same for zirconium and scandium, there's some variations. All right, and so this, I guess I just had, when I did my slides in the weekend, I did that, so that's not in the paper, but can this composition variation be explained by solidification microsegregation? So just took a really simple shell model, and these fits were done by Robson in study in 2004, where he looked at microsegregation of scandium and zirconium during solidification, and just use this simple model, one dimension, to fit the variation, and that's the value of the fitting parameter here for zirconium and scandium. So in our case, put it in the bottom of the graph because I will add magnesium and silicon after. So that's the two curves from Robson. So then I just thought, so for each sample, we have a scandium and zirc content. So let's try to place them on the curve to see if they could be solidified at different times. So here you see the weight percent, the content of the single aluminum phase, so alpha aluminum phase, as a function of the mole fraction of solids so during solidification. And then you can see that if you try to place these 3 atom probe samples, so the last sample actually had higher scandium than zirconium, so you had the reverse effect, which made me think that they would be in the last one to solidify. That if you add on these 3 atom probe samples, the magnesium and silicon content, and do a fit, so that's not the best fit. I mean, it's 3 points, but I think it can show an interesting trend, and especially what we noticed before, that the magnesium to silicon in the third sample they were really close together, the content, which also make me think that they solidify last. Also explaining that in this region you had also some magnesium silicon precipitates forming, and also higher density of aluminum 3 scandium dispersoids. And here you had the fitting parameters. So then now let's look at the dispersoids composition in this ASCAS. So that's some Proxygram. I have to apologize, it's quite small. I took them from the paper. But what we see mainly is that these dispersoids here, if you look at the composition gradient from the 3 samples, so that's sample 1, 2, and 3, they have a similar content in scandium and silicon, so really high in silicon. For this type of dispersoids, and also at the interface in segregation of different elements, so magnesium, silicon, and copper mainly, and really low zirconium content. So more zirconium is about 0.618%, so more than in the matrix, but still really low. That's the composition of each single dispersoid in these 3 volumes. And what we saw, it's actually to find the stoichiometry. So that was the result from the paper here, and that's this new volume here. You actually see that 75% of your aluminium-3 scandium dispersoids are aluminium and silicon, and about 20% of the aluminium is substituted by silicon here. And then the rest is scandium and zirconium, and of course you had a few elements here, but mainly scandium. And in this volume here, the dispersoids were a bit higher in silicon, but that could be an effect of this nucleation as well as interfacial effect, that it looks like it's higher. But it's mainly the same, really about 20% silicon substituting in the dispersoid. So now there have been a lot of work by mainly one group in Northwestern looking at the effect of silicon content on scandium dispersoids formation in low silicon containing alloys, so not really in high silicon alloys. So that's the different studies here, which are referenced here. That's the compositions they looked at. So starting from really low silicon content, all the way to 0.18, and that's our study with 0.6. So now I've took all the other papers, and they use atom probe tomography as well, and look at the composition of the dispersoids reported in all their papers for the different composition. And what you can see is that if you look at, so most papers were aged at 300 degrees C, the samples, but a few were not 300 degrees C, so I put them back. And if you put them on an equivalent time at 300 degrees C, you can see that the silicon to aluminum ratio actually decreases, and it's not really related to the bulk composition in silicon, so it seems to happen in all these alloys. And if you look in our case, which is really as cast, so if you put it at 0 hours, you could see that it could fit in the top of the curve here. So really, it confirms that silicon plays a really important role in the first step of precipitation, so in the nucleation and initial growth of dispersoids. Now let's look again at this thermomechanical treatment. So here I've put some random steps here, just so that's what we're doing at the moment. The ongoing research at Deakin is really looking at trying to homogenize these alloys, and it's not that easy. So we have a complex as-cast microstructure. So what do we do from there? Do we homogenize traditionally from, we have already dispersoids in there? One of the questions is, can we solutionize these alloys? So of course, then we're limited in composition. We can only have quite low magnesium and silicon content to find a solid solution, a full solid solution in these alloys. And if we solutionize, how important is the cooling rate after solution treatment? Because here in the industry, you'll have limitations. Might not be, if you're looking at feasibility, industrial feasibility, might not be feasible to water quench, for example. Then how many steps are required after that as well? So that's a lot of the questions we're trying to answer. Now if we look at the, so if we remove all the precipitates from our 3 atom probe tomography samples and look at solid solution, you can see solid solution for the different samples here, and that's the average solid solution reported and the bulk composition of the alloys. You can see, for example, that the scandium in solid solution in the, so that's in the interdendritic region, the last part of the samples to solidify. It's actually no scandium left in solid solution. So in these areas, which were rich in also magnesium and silicon, all the dispersoids formed. But if you look at to take an average from these 3 samples, you can see that actually you still have quite a fair amount of scandium and zirc. If we trust these numbers, of course, it's 3 atom probe tomography samples, so it could be arguable that it represents the bulk solid solution, but still it gives an idea that there's quite a lot left in solid solution. Yeah, so you can see that, yeah, again, the local composition heterogeneities are highlighted. Some of the conclusions from my talk, so we characterize the as-cast dispersoids in these alloys. I know that, yeah, to study microsegregation atom probe is quite non-traditional, but I had the atom probe data, so I had to look if we could actually get an idea of microsegregation, but it'd be good actually to try to confirm that just doing some quantitative EDX or microprobe type measurements. But I think that, we at least highlighted that there's variations in compositions in the microstructure. And then we also observed the formation of magnesium-silicon type precipitates. And I guess one of the conclusions is probably we will need for these alloys a non-traditional homogenization treatment. So just quickly, a bit more publicity for the talks from Deakin at the conference. So we have a poster from Steve this afternoon on his results from his PhD. Because it's the World Cup, I thought, I should show at Deakin that we have different nationalities. So Steve is from Australia. Luckily, France beat Australia, so otherwise I would have struggled to go back to work next Monday. Then another talk tomorrow from Baptiste. So Baptiste is another French guy. We have quite a few now at Deakin, quite a few big French representation. Then we have two speakers. So Catherine is not here, but I will present on her behalf, and Andreas from Germany. So Andreas made it today despite the Mexico win yesterday, but that's okay. And then finally, Ali, again, didn't make it to the conference because he didn't get a visa. He was refused his visa because he's from Iran, which I found pretty outraging, but I'll be presenting on his behalf as well. So I have two more talks, but feel free to write down these talks. Thank you very much. Yeah, no,